If you follow space news, you see the headline every few months. Astronomers have found a new biggest galaxy ever discovered. But these announcements rarely explain what biggest actually means when you are measuring the void of space. We usually grasp these concepts by anchoring them to human metrics. A high-speed bullet train reaches roughly 600 kilometers per hour. Light travels about 1.8 million times faster than that. That speed is unimaginable on Earth. But once you leave our atmosphere, the speed of light begins to feel restrictive. If you took that bullet train to the Kuiper Belt, the distant region where Pluto orbits, the trip would take more than 100 years. To manage these gaps, astronomers use the light year. This is the distance light travels in 1 year, which is approximately 9.4 trillion kilometers. Because human-scale measurements like kilometers result in numbers too large to process, mapping the cosmos requires us to switch to these time-based distance metrics. To understand the scale of a galaxy, we have to look at how far its radiation reaches. Our own Milky Way is the starting point, measuring roughly 100,000 light-years from one edge to the other. However, distance alone is a misleading metric for determining which object is the most significant. Astrophysicists use 3 benchmarks to measure a galaxy's footprint: visible light from stars, radio emissions from gas, and total gravitational influence. Popular headlines often focus on the single metric producing the largest number, which obscures the actual physical reality of the object. This creates a trade-off between measuring stellar density, the actual physical matter, versus radio emissions, which measure energy volume. To accurately evaluate these cosmic giants, we have to look past the simple diameter and ask exactly what is filling that space. For decades, the benchmark for scale was IC 1101. It is a massive structure, measuring 6 million light-years in diameter. IC 1101 is defined by its optical star clusters. It is a tangible collection of physical matter containing an estimated 100 trillion stars. While counting stars provides a clear physical map, keeping that many suns in a single cluster requires an immense gravitational anchor. The engine at the center of IC 1101 is a supermassive black hole with a mass 40 billion times that of our Sun. Measuring by stellar mass identifies the heavyweights of the universe, but it prioritizes dense physical reality over total spatial volume. A new challenger called Alcyoneus recently surpassed IC 1101, claiming a diameter of 16.3 million light-years. This record wasn't set by counting stars. Alcyoneus is a radio galaxy, meaning its size is determined by its energy output. Astronomers mapped this structure using the LOFAR network in Europe, which uses 20,000 radio antennas to detect low-frequency emissions invisible to the eye. Most of that 16.3 million light-year diameter consists of invisible plasma and plumes of energy. There is very little physical stellar matter compared to the space the plumes occupy. We can compare these two physical realities directly to see where the discrepancy lies. IC 1101 was discovered through optical observation at 6 million light-years, while Alcyoneus was mapped via radio waves at 16.3 million. However, IC 1101 contains vastly more stars and a more massive central black hole. Alcyoneus is larger in volume, but IC 1101 is significantly denser in terms of matter. If you decide to call Alcyoneus the biggest, you are measuring the reach of the black hole's exhaust. If you choose IC 1101, you are measuring the engine itself. This suggests that biggest is a subjective term. The answer depends on whether you value raw matter or spatial influence. We can categorize these giants using a quadrant chart, mapping measurement tangibility against cosmic impact. Prioritizing physical stars places IC 1101 in the top right, representing the highest concentration of matter. If you value energy reach, Alcyoneus sits in the top left, maximizing radiation boundaries. Placing our 100,000 light-year Milky Way on this chart provides perspective. Compared to these structures, our home is a modest, medium-sized collection of stars. While we lack physical scale, we are the ones capable of detecting these invisible structures. Using continental antenna arrays, we can map plasma plumes 3 billion light-years away that would otherwise be lost to the void. We are physically microscopic, but we serve as the only known rational observers capable of mapping these giants. The universe may be dominated by massive engines and energy plumes, but it is our responsibility to interpret and understand them.